And in general, I was not supposed to be here on stage. It's just because of some last-minute changes in the program, so I had to replace the speaker. But I'm very happy because it gives me a chance to teach a topic which I believe to be very important, and it is not covered in sufficient detail in the program. And before I begin, I should say, so my affiliation is Telecom Paris. So a lot of people ask me that. It has nothing to do with France Telecom. It's not a company. It's what they call in France grande école. So it's a technical university. It's an engineering school, high engineering school, and it's pretty advanced. So since recently we merged with École Polytechnique, which is considered to be the most prestigious engineering school in France. And we have a doctoral school, so it's just for the people who think of a research career and who want to spend a few years in France, in Paris. So I have an open position for related to evolution of blockchains. So it's a very cool, very interesting topic, I think. So if you're interested, just talk to me after the class. Okay. Lower bounds. So I presume that most of you deal with programming on the regular basis. So when you write a program, how do you know that your program is efficient? Is there like a standard way of saying, I did my job well, my program runs well? What do you do? Sorry? Well, big O notation is good, but still, I mean, you would go for a formal complexity analysis. You would try to see what's the worst case complexity of your program. Well, otherwise, I mean, what can you do? You know, you can run it, and if the user is happy, you would say it's good. Requirements. So there are some formal requirements which if you meet the requirements, it's good. Yeah, and the requirements are set by the users, well, by the application or whatever. It's good. Yeah, well, it's usually the case. But sometimes you might want to know if your program is optimal in whatever sense. Yeah, we would like to see if you could do better. So for that you need a metric, of course, and a way of computing this metric for your program. So and this is exactly what we are going to talk about. So we're going to talk about, well, unlike previous classes where we discussed concrete algorithms and we studied the pseudocode and we saw, okay, now we don't really study the algorithms, we study the problem. So we focus on the problem and we try to see what are the inherent costs of an algorithm solving this problem, of any algorithm. Okay, so and there are some interesting techniques of establishing lower bounds. And this class is mostly on techniques, not on the results. It's more we try to see on the examples of concrete results, which are classical results in distributed computing. We try to see what are the major tools we can use to discover these inherent costs. Okay, and typically we are looking for lower bounds which we can hit, unlike this guy on the picture. So we are looking for something which is tight. Yeah, so it's not only we find something which is necessary to solve a problem, but we will try to show that this is also sufficient to solve the problem. Yeah, so in this sense, we were looking for optimal complexity for a specific problem. Okay. So, well, as we know already, not everything can be computed in the distributed environment. Yeah, so there are some problems which cannot be solved. For example, the problem of consensus cannot be solved deterministically in an asynchronous system. Yeah? But if something can be computed or can be solved, what are the costs? Okay, and for that we need to understand what is the metric we are interested in. Yeah? So in our domain we talk about step complexity, memory requirements, and typically, as you say, it's a big O notation. Well, actually, for lower bound, it's rather a big omega notation. Yeah? And typically it's asymptotic with respect to what? With respect to the system size. Yeah. So the larger is the system, typically the larger is complexity of your program. Okay. So this is what we understand as a required cost. We use the omega notation for that. Yeah. So typically we look for upper bounds, which are the costs of the concrete algorithms. Yeah. And if these two costs coincide, this is a holy grail for us. It's a tight bound. Okay. And all the bounds I'm going to discuss in this class are tight, well, magically. Well, not magically, but thanks to the researchers who established it. Okay. Well, the difficulty here, unlike the classical complexity theory for sequential computing, here, well, there are different opinions, but I still believe that there are many models. Yeah, it's not like one model which tells it all. There are many models. There are multiple parameters of this. Well, I can just put a jungle here. It's not as friendly as in the picture. So we have different communication primitives. Yeah, we can go from message passing to shared memory objects. And the shared memory objects, you start with read-write, but you can enrich your model with some stronger primitives, and that creates some advantages sometimes for complexity. Well, you can communicate through message passing. You should make some synchrony assumptions. You can go from asynchronous to synchronous through some a variety of partially synchronous models, some models which are not purely asynchronous, not purely synchronous. Okay. You have fault models. Yeah, you have different kinds of failures, and typically the easiest failure to deal with is a crash failure, where a process just stops taking steps. And you have emission failures, where the process, for example, doesn't fail indefinitely, but it fails to perform some actions. For example, send messages. Yeah, so this is what we call send emission, or it fails to receive a message, for example, because its receive buffer is overflown. Okay. And then you have Byzantine behavior, which is completely arbitrary. We make no assumptions about the faulty nodes whatsoever. Okay. Complexity metrics. Okay. Generally, we talk about time complexity, which is measured in terms of the number of steps a process should perform to complete an operation, for example. Right? The number of rounds, if the model is somewhat synchronous, the number of rounds you need to perform of communication before something happens, something desirable happens, or message delays. If the system is asynchronous, you cannot really define a well understood notion of a round. You reason in terms of message hops. Okay. Space complexity is about resources you use. Yeah. How many memory locations are required? Okay. How many messages you need to transmit? Sometimes you're interested in how much information you need to transmit. Yeah. For example, Ashur yesterday discussed the solutions of the Byzantine agreement problem. And actually, thanks to Ashur and his colleagues, we now have an optimal Byzantine agreement algorithm with optimal resilience and optimal communication complexity. Yeah, n-square communication complexity. Okay, and actually, this is an interesting example of a problem for which the lower bound was established before the upper bound. So the algorithms we are going to discuss now, it was the opposite. So they first found the algorithms, and then they established the lower bound. Then they showed that the algorithms were optimal. And sometimes this takes a long time to prove that the algorithm is optimal. You should ask me something. Well, so what's missing here? Again, coming back to performance, especially in the concurrent computing world, which is neither really time complexity nor space complexity. What you might be interested in. Synchronization time. Well, you can probably say it's a time complexity. You measure time, but what else you can measure? Resilience. But resilience typically is set in advance. It's not something. It's a property of an algorithm. Okay, so it's a priori you define how many failures you can tolerate.
Consider concurrent algorithms, we usually suppose number of rounds and number of
Yes, yeah, okay, yeah, but okay, you may think of joint metrics. Yes, 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 yeah, yeah. CPU utilization, okay, not exactly. uh, what do you mean by the topology of a network? What is it? Yeah, but it's again, to me it's more like a property of the environment rather than the algorithm. Yeah. Yeah. Throughput. I was looking for throughput. Thank you. So no, actually, I think everything can be reduced more or less to time and space, but throughput is something special. Throughput is the amount of work you perform per time unit. And this is actually one of the most important characteristics in concurrent data structures. How many operations you can perform in time unit. Yeah? So this is something which I'm not going to discuss, because this class is going to be about worst case complexity, and analyzing throughput in the worst case is completely useless, because throughput is an average characteristic. You count the number of operations over a long period of time, and then you divide it by time, and then you get the throughput. And for formal analysis of throughput, you need some notion of some stochastic model of your systems. Like you need to make some assumptions about the scheduler, how processes are ordered in the execution. And this requires some probabilistic analysis. And if you're interested in this, Vitaly Aksionov is running somewhere around. You can bug him about this. So he has some interesting ideas about how to build stochastic models of throughput, of analyzing performance of a concurrent data structure, of a concurrent program. Okay, so what I put in this course? Generally, we are going to discuss, well, 3 results. Yeah. It's not really about results, it's about techniques. So we start with the covering technique. Yeah, so how to discover the space and time complexity of a program using the notion of a covering. So how many processes can cover specific memory locations. And based on this, we can somehow deduce some idea about how many memory locations are required. Then we switch to consensus. Actually, well, this is something which also has been discussed so far. The FLP result, the impossibility of consensus, is based on the notion of a valency. It's a potential decision values in a specific state of a protocol. And we use this both covering and valency together to establish a lower bound on space required for solving consensus. Well, not consensus per se, what we call abstraction-free consensus. And finally, we go to something very interesting, and we come back to the classical problem of mutual exclusion, and we try to discover the total work complexity, which is somewhat related to throughput, but not immediately, for a mutual exclusion algorithm, using a very interesting, very original information theoretic algorithm based on decoding and coding. Okay, so covering. And by the way, just to jump in with your questions anytime. So we are back to the shared memory context. We have a bunch of processes like P1 to Pn who communicate through invoking operations on shared objects. And for the moment, we assume that these operations are read and write. And the shared memory locations can be written and read by any processor. So there's no real a priori assignment who can write where. And actually, it makes sense for the space complexity, because we are interested in the minimal amount of memory we need to allocate to implement a specific object. And the object we are going to consider, well, we're not there yet, but the object we are going to consider is called a counter. So we know already that a counter cannot be implemented read-write in a wait-free way. So, well, some of you might know this, but this fact has been mentioned by Danny Handler in the first lecture. What is covering? So we consider an algorithm, as I say, every process can write to any memory location assigned to the algorithm. It may happen that at a given moment of time, a number of processes is trying to write to the same location. Or we can say, in a given, you fix a moment of time and you see that, okay, you have a set of processes and they cover, well, they are about to write to different locations. And the idea intuitively is that if you want to be noticed, you need to write to something which is not covered. Because if you only write to something which is covered by other processes, when you finish your operation, you can schedule this process to perform their writes, and all traces of your operations disappear. Okay? So this is roughly the idea of how to establish a lower bound. Yeah? How to show that you need more locations. Yeah, if you can find a situation where a certain number of memory locations are covered, you can immediately say that and you have some process which you can run. You can squeeze the steps of this process just before these guys perform their write operations and show that this process to complete an operation should write somewhere which is not covered. Okay. So this is somewhat related. I don't know. It looks like a little bit like a musical chair game where you have less chairs than processes, and if multiple processes write to the same place, at least one of them overwrites what the other has written. Okay. So there is a little bit of formalism. So we have this notion of a block write. So it's a block write as a part of your execution in which a set of processes perform a sequence of writes to distinct memory locations. Okay, so for example, we can consider a specific configuration C. Yeah, the configuration for us is just the state of the protocol at some point of an execution. And imagine that at this point of the execution, we have processes P1 to PR who are about to write to distinct registers, distinct locations B1 to BR. Yeah, we say that B1 to BR are covered by these processes. Okay? And an extension of this configuration with these writes of this R process, it's called a block write. It's just, we just let them write. Okay? And we get a new configuration, which is C extended with this beta. Beta is just these steps of these R processes. Okay? And then we imagine that after we completed this block write, we let some process Pn, which is not part of this P1 to PR, run solo without contention, perform its steps until it completes an operation. And in most protocols we consider in this class, this is a requirement. If you run in isolation sufficiently long, you should complete your operation. Yeah, this is a weaker form of liveness, weaker than wait freedom or non-blocking liveness, which guarantees your progress only to the processes which run in isolation. Okay, and this is the case here. So it runs solo and completes some operation. Remember that I didn't say which problem we solve. It's just in some abstract hand waving so far. Okay, imagine it completed the operation. So what I can do, I can take the process PR plus 1, which is not member of this group, and it's not Pn. Yeah, imagine that R is less than n minus 1. So you have these guys, you just let it run solo just before the block write. Yeah, there's some schedule alpha which extends configuration C, let it run solo. Okay, so what I can say? I can say that if PR plus 1 must be seen by Pn for some reason, yeah, for example, because of correctness of the program, it should write somewhere outside of this set of registers. Okay? Well, it's important because if it only writes to registers B1 to BR, then this block write would hide any trace of its execution. And then Pn would simply not notice it. Okay? So this is roughly the idea of all this covering argument. Yeah. So now we are going to some concrete result. Actually, it's much more general than the problem I'm going to present here. First of all, because they talk about they don't talk about some concrete data structure. They talk about a class of implementations, which they call perturbable objects, and they also consider a model in which you have randomization. You can actually toss a coin whenever you execute a step. So now we simplify a little bit. We consider a specific data structure, which is a counter, and we assume deterministic algorithms. But we should keep in mind that all this can be easily generalized to the case of perturbable objects with a randomized algorithm. Okay. So we talk about an abstraction-free implementation of a counter. Yeah, so what is a counter? A counter is an object where you have just one operation. Well, it's like what Danny called fetch and add object. Here is fetch and increment. So what you do, in one atomic operation, you read a state of the memory location, and you increment it and write it back. Okay, write the incremented value back in one atomic step. Okay, so intuitively, this is something which is more powerful than a register. Well, in some sense. For example, you can use it to solve consensus among two processes. Yeah, how? Well, imagine that it's initialized to 0. The first process to come performs an increment operation. What it gets as a result is 0, the initial state. After it completes its increment operation, the state is 1. Yeah, then the second process to come would observe state 1 as the value of the counter and would see that he was not the first. So this way you break the symmetry between the two processes. One of the two processes always wins, meaning that it was the first to access the counter, and the second always loses. Yeah, and this way you always decide the value of the winner. Yeah, so if you come back to this topological representation of the space of executions, what you have is something like this. Yeah, so instead of 3 intervals, you only have 2. Yeah, this interval in the middle where both processes are losers is excluded. Okay, so what does it mean for us? It means that you cannot implement a counter using reads and writes, because we know that consensus cannot be solved using reads and writes in the asynchronous system, and by reduction we deduce that counter cannot be implemented by read and write, because counter can be used to solve consensus. Okay, so there's no weight-free implementation of a counter. Okay, so that's why we have this relaxation of weight freedom. We say it can be implemented abstraction-free, and in fact, any object can be implemented abstraction-free using reads and writes. Okay, because abstraction freedom is a pretty weak liveness condition. Okay, I hope I didn't lose you so far. Okay, so I'll give an example of what abstraction freedom is. Okay, so our result. So every implementation, every abstraction-free implementation of a counter using reads and writes, using read-write operations, has space complexity at least n-1, and solo step complexity at least n-1. So what is a solo step complexity? Is the number of steps a process running solo should perform in the worst case to complete an increment operation. Okay, so you have linear space complexity and linear time complexity. Yes? N is the number of processes, yes. Yeah. So N by default in the whole class is the number of processes. So it's linear with respect to the system size. Okay? So the more contention you can observe, the more space you need. Okay? And actually, this lower bound is tight. Yeah, so there is a paper which is already 10 years old, which shows that any abstraction-free implementation, well, no, which gives an algorithm for counter and a large class of objects, which is using linear time and linear space, and this shows that the lower bound is tight. Okay, so I'm using this holy grail sign to show that it's tight. Okay, what's abstraction freedom? It's a condition which says well, you're not obliged to terminate in all executions. However, if it happens that from some point on, there is some process which runs in isolation, which means that, okay, you have 3 processes which started the operations, they perform some steps. Yeah, so this is the usual way we decrypt the executions. We have the time flow and we have steps. Yeah, so these guys take steps. And from some point on, there is only one process running solo. So abstraction freedom says, if this is the case, then this process is supposed to terminate eventually. Yeah? And what we count here is this number of steps. This is what we call solo step complexity. Okay? So it's supposed to terminate. Right, so coming back to the model assumption, yes, so you have n processes, P1 to Pn, reading and writing to shared objects, shared memory locations. We consider a deterministic algorithm implementing a counter. As I said, this is not a very important limitation. We can generalize it. but it's easier to explain. Okay, and we assume that every process just constantly run increment operations. We just consider a subset of executions in which you constantly, whenever you complete one increment operation, you immediately invoke the other, and so on, and so on, and so on. So you have the a priori assignment of operations to processes. And thanks to that, we can represent a state of the system is just a sequence of process identifiers. It's just a sequence which specifies the order in which processes take steps. Okay, so this notation, pi star, means that all sequences of elements in pi, all finite sequences. Yeah, so every configuration, every reachable configuration of our protocol, no matter which protocol, which algorithm I consider, yeah, the configuration is specified just by a sequence of steps. And give me a sequence of steps, I tell you precisely what is the state of the system. Okay, because the algorithm is deterministic, the memory itself is deterministic, so everything is defined by the schedule. We call it the schedule, or execution, doesn't matter. Okay? So we proceed by induction, and we use the covering argument in every step of this induction. Yeah, so what we're going to prove? So we're going to prove that for each k from 0 to n-1, yeah, n-1 is our goal, there exist schedules. Well, schedules or executions, it's like sequences of process identifiers, alpha k, beta k, and gamma k, yeah, such that, okay. So alpha k is the schedule of processes p1 to pn-1. You always keep pn to run it at the end. Yeah. Beta k is a block write. Well, it's not necessarily a block write, but I think it's convenient to imagine that's a block write. So there are some corner cases in which it doesn't have to be block write. But what's important is that just it's a sequence of IDs from Q1 to Qk in this set of P1 to Pn-1. So it's a set of all the processes except for Pn. Okay? Yeah, block write is a sequence of write operations to distinct memory locations performed by distinct processes. Okay? But here it's typically block write, but it doesn't have to be. Yeah, in some weird cases it doesn't have to be, but it's not important for the moment. Okay, so it's intuitively what happens here is you hide everything which is done on B1 to Bk up to this point. Yeah, if you run this fragment of an execution, and then finally gamma k is an execution of Pn, in which exactly processes B1 to Bk are accessed and no other objects are accessed. Okay? K is the parameter of the induction. Yeah, and so for each k from 0 to n-1, I can construct this kind of an execution. And remember that my goal is to establish solo step complexity of the algorithm and space complexity, how many registers I use. And if I can construct this kind of an execution for k equals n-1, I'm done, because what I have Pn running solo here and accessing exactly n-1 registers, and of course I use n-1 registers, right? So this is my goal, right? So this is what I want to establish, okay? Right, and what's important here is that I can actually run, well, additionally, what the property of this, this is what I need for induction. The property of this construction is that whatever lambda k I run within this, just before this, what we call a block write beta k, yeah, by this process pi minus all the processes I use in this beta k, yeah, everything but Pn and Q1 to Qk, so everything which is left. If I run it here, then the states of B1 to Bk are exactly the same in this execution as in the execution without this lambda. Yeah, so whatever I do here by these processes will be not noticed by Pn in gamma k. Okay? So this is what I want to construct inductively. Yeah? My goal, of course, is to reach the point where k equals n-1. Yes? Sorry, I don't hear. Yeah. Yeah, so what's happening? Good. So, okay, so this is my goal. I want to construct a specific execution. Yeah? So in this specific execution, I have a prefix alpha k, in which something happens. What's important is that Pn doesn't participate in alpha k. Yeah. I extend this prefix with the short fragment beta k, which is executed by q1 to qk, some selected set of k processes from this set p1 to pn minus 1. Yeah? In this fragment, each of these processes q1 to qk performs exactly one step. Okay? Intuitively, it's a step, it's a write on some register in b1 to bk, but not always, as I said. And then you extend it with a solo execution of pn. Okay? And what's important is that in this execution, pn accesses exactly k registers, b1 to bk, the same registers which are sort of covered here. Okay? So if I reach k equals n minus 1, I'm done. An additional requirement is that if I insert here any execution lambda k by all the processes which are not pn and not q1 to qk, pn wouldn't notice it in gamma k. Okay? Does it make sense? Well, it's not the question of why. I just say that I can construct it. It's a requirement. I will show you how to construct it, but I'm not. It's not a theorem yet. Okay. Right. So the base case is easy. Everything is empty. Nobody does anything. Yeah. No registers are covered. Everything is fine. Yeah. So it's all executions are empty. Yeah. So far so good. I just start with the initial state. Yeah. Right. So now, suppose for some k less than n minus 1, I have my construction. Yeah, I want to take one more step. Okay. So what I say, I can extend this gamma k, which I had before here. I can let it run until it completes the increment operation. Why it should complete? Because it's an abstraction-free execution algorithm. So in an abstraction-free algorithm, if I run solo, I eventually complete the operation. So this gamma, you can just let it run until it completes. So my claim is that Pn, if it runs solo after this step, after this configuration, it should access some other object rather than bk plus 1. Well, it's sort of natural, because if it doesn't access any object of, outside of b1 to bk, then actually you may squeeze some operations here which perturb the outcome of this operation. Well, it's not that obvious yet, but we'll see. We'll come to that. Okay. But so far, I can squeeze any operation, any execution lambda k here by this processes pi minus q1 to qk ppn. Remember that k is less than n minus 1, which means that there is at least one process here, which I can use. Okay. Right. Suppose not. Suppose Pn returns some value v by performing the increment operation here without consulting any object outside of this set, outside of b1 to bk. Yeah, just imagine. Right. So this is my situation. So this is a sort of a block write here. After the block write, I access only b1 to bk, return v. What can I do? How can I perturb? How can I make sure that this value v is incorrect in this execution? What can I do? Well, of course, I need to insert something here. But what exactly? What do you think? So I want to ensure that in no circumstances v is a correct output. So v cannot be returned. It's a counter, remember. It's a, well, I should say it's a linearizable counter, which means that I can always find some linear order of operations so that everything respects the sequential specification. So what do I choose here? I can insert whatever I like. I should increment, yeah, but just one increment? V increments, exactly. If I put V increments, I know that I already incremented the counter up to V. I cannot return V again. Yeah, it should be at least V plus 1. Okay, so what I do is, exactly, I squeeze v plus 1 increment operations by some process in this set. As I said, k is less than n minus 1. I have some process at my disposal. Okay, so I complete this v plus 1 operations. Well, v plus 1 to be sure, but I think v might work too. And then I return v here, not linearizable. I cannot linearize it. And because I have two operations which return basically the same value. And the counter doesn't allow me to do this. Okay? Okay, so the conclusion is that indeed Pn running solo from this point should access at least one register outside of this set. Well, let's call it bk plus 1. So what we do, we just extend how we define gamma k plus 1 to build the induction step. We extend gamma k until Pn accesses some bk plus 1 outside of the set, and we just stop here. So far we construct an execution in which exactly k plus 1 objects are accessed in a solo execution of Pn. Okay? Now, this is a slightly subtle case, and this is why actually I said it's sort of block write, but not always. It might be stupid to access some object bk plus 1. For example, it's some object which is never written by preceding operations. Well, it's completely useless, but it may happen. So for that, I say it may happen that no execution alpha k, no extension of alpha k by steps of this process p minus, well, I already use q1 to qk. I use some other processes here. And no extension writes to bk plus 1. In this case, everything works. But if there is an extension in which bk plus 1 is written after alpha k, I just let it run until it is about to write to bk plus 1. And of course, I use this write to put as a part of beta k. Yeah, just this is how I extend beta k. So now I get beta k plus 1. If this is not the case, yeah, I just take any step of processes in this set, of some process, yeah, and add this step here. Yeah. I talk about the both. So okay, so for alpha k, if we imagine that alpha k is in some extension of alpha k writes to bk plus 1, I just let it extend it until it is about to write to bk plus 1. This is my alpha k plus 1 now, and this last step, which is the write to bk plus 1, I put it as a part of beta k. Okay? If this is not the case, if nobody writes to bk plus 1, which in some sense means that Pn does something stupid, it reads something which is never written, which is allowable. Yeah, we can allow it in an algorithm. So in this case, I just stupidly add any step of some process qk plus 1 as a part of beta k. In both cases, remember, either I cover an object, which is read here, or accessed here, it doesn't matter, or I use the object which doesn't change its state. So it's in both cases, what I have is no matter what thing I insert here, the Pn wouldn't see the difference. Okay? Well, sorry. And this is my beta k now. So beta k is q1 to qk as before, plus this step of qk plus 1, which is either the process which is about to write to the object bk plus 1, or any process if nobody writes to bk plus 1. Yes? Right. Well, this is, you see, as I say, either you cover bk plus 1. Yeah. In this case, Pn wouldn't actually see the difference if you insert something which writes to b1 to bk and bk plus 1. Yeah, no matter what you insert, because Pn only accesses these k plus 1 objects. Or nobody writes to it, in which case it's in an initial state. And again, Pn doesn't see the difference. Yeah, well, I know it's subtle, but this is the argument. Yeah, so I construct it iteratively like this. So as a result, what I get is I get my induction hypothesis extended to the case of k plus 1. Okay. Well, and I'm done. Yes, actually, this is the whole proof. So I'm done. What I constructed is an inductive step. I constructed the base case. I reached the state k equals n minus 1, and I'm done. I have step complexity linear, space complexity linear. Yeah. Oh. Yeah. Okay. It's important, yeah. So because we are going to use this. Yeah. So this is our induction hypothesis. Yeah. So we start with well, we show that for each k from 0 to n minus 1, we have these 3 executions, yeah, alpha k, beta k, gamma k, yeah, such that alpha k is all execution of some processes except for Pn. Gamma k is the sole execution of Pn. Beta k is some short fragment in which processes Q1 to Qk execute 1 step each. Okay. Additionally, I say that gamma k is this execution in which Pn accesses only objects B1 to Bk. Yeah, some k objects accessed by Pn. And the additional requirement for this execution is that whatever I insert here by processes not used in this beta k and not Pn, the states of B1 to Bk, which are the only objects accessed by Pn in gamma k, will be unchanged. For 2 reasons. Either they are covered by beta k, yeah, means that some process from Q1 to Qk writes to this object, or they are just never written. They are just in the initial state. No, it's not the goal. It's an argument. It's part of the argument. So we show that if Pn in the inductive step doesn't access any additional object here, Bk plus 1, then the algorithm is not linearizable. Yeah, we establish a contradiction assuming something by contradiction. So there are 2 instruments here. One is the induction, the other one is reasoning by contradiction. In each inductive step, by contradiction, I show that Pn should access more objects. Yeah, so this is what my goal. I want to show that I need to use more memory and I need to perform more steps. Okay? Oh, because I ran out of processes. I cannot use any process here to perturb the computation. Yeah. Okay? Oh, there's no P0, P1 to Pn, sorry. It's K starts with 0. In this case, the base case is just empty. There are no steps at all, which is okay. So no objects are covered, 0 objects are used, 0 steps are taken. Okay, so it's a stupid base case, which is good enough for me. Okay? Sorry, I don't hear. The previous one, yeah. Sorry, what? Well, as I say, this is good. This is a good assumption. It works, but it's not always the case. It doesn't have to be always the case. Yeah, but I think it's a good intuition to assume that they just write to these objects. But as I say, sometimes the algorithm can be stupid enough to not to use some objects, not to write to them. And I have to account for this case, and that's why in the inductive construction, I have this special case when no extension of alpha k writes to Bk plus 1. In this case, any step would serve. I can just put any process. Okay? Yes.
We have proved that we should access at least n registers, and therefore we have at least n access
steps.
Yeah, n steps. Yeah. Okay.
Yeah. N minus 1 to be precise. Yeah. So it's with n. But all the algorithms which solve, for example, counter use n. So there is some little annoying gap in this. But asymptotically, it's the same. It's linear, so we are happy enough. Okay? Yes. What's Q or Q1? You mean Q1 to QK? These are processes. This is some processes which I use, and this is how I choose this process. So if there is extension of alpha k in which you write to bk plus 1, I choose some process from the set of processes I haven't used yet, and this is the process who is the first to write to bk plus 1. Yeah, I just wait until some process writes to bk plus 1, and this is the process I'm going to use. Okay? Okay, so thank you. So actually, as I said, the only point where I used the fact that it's a counter was to show the contradiction. And in fact, I can generalize this argument to a class of objects. And this is what Jayanti and Toyeg, and Jayanti Tan and Toyeg established as a class of perturbable objects. So you can insert some execution fragment so that the resulting solo execution of Pn is perturbed, should decide something else. So here you have alpha, beta, gamma. There is some schedule alpha, beta, gamma, such that alpha and beta do not contain Pn. Gamma is solo execution of Pn. Beta is some proper subset by proper subset of this. Proper meaning that there's at least one guy outside of which is not used in beta, which is a member of this set. And yeah, so you can insert some solo execution of the process outside of this set, which is not in beta, and Pn is supposed to notice it. Pn should return different results depending on whether you have this this perturbing execution lambda or not. So it's basically the same what we used so far. Yeah. Alpha, lambda, beta, it should be gamma, of course. Yeah, sorry. So this is gamma here and gamma here. Yeah, of course. Sorry. Thanks. Okay, so so what I'm saying is that linear lower bound on space and solo step complexity holds for any perturbable objects, any perturbable object in the abstraction-free implementation, even if you use randomization. Yeah, so it's not immediately obvious, but in fact, what randomization is that in every step you toss a coin. And when you look for a step complexity, in worst case step complexity, yeah, you just need to show that for some sequence of coin tosses, you have to access n registers and perform n steps. So it's and you can do it. You can prove it. That's what I mean. Okay. And the perturbable objects, aside from counters, it's actually, I don't know, the atomic snapshots, compare and swaps, and so on. So these are all objects in which you have some conditional. So whatever you return, you can insert you change the state of the object. You're supposed to return something else. Okay. So now we take a step a little bit further. So in addition to covering, we're going to use what people call valency. Yeah, so valency arguments. And I'm talking about a beautiful paper by Leki Zhu, where he established a linear lower bound on space complexity for consensus. Again, for abstraction-free consensus. Yeah, as we know that in general, there's no solution for weight-free consensus on unblocking. We talk about abstraction-free. And actually, again, the algorithm for abstraction-free consensus has been known long ago, but this lower bound has been established recently, a few years back. And this is a beautiful paper because it's very short, very precise, and the proof out of 6 pages, the proof takes like 2 pages. So and it doesn't require anything for you any background. You just read it and you enjoy it. So I highly recommend. Okay, and the argument is beautiful. Okay, so the space complexity of any abstraction-free consensus is n-1. And yeah, as we know, it's tight. And it applies to randomized algorithms too. Well, as Ashur taught us yesterday, there are 2 ways of making consensus work. either you relax the liveness assumption, or you, for example, you use randomization. You can, or you make some additional assumptions about the environment. So for all these assumptions, this lower bound applies. And because you see, for the lower bound, it's very convenient to choose a weak progress guarantee, because you say even for a weak progress guarantee, you have these space constraints. So if you have a stronger progress guarantee, of course you need the same space complexity. Yes.
Implementation should use only write and read registers.
No. You can use, yeah, but this lower bound is about read and write.
So no CAS, no.
Well, if you have a CAS, if you think about it, if you have a CAS,
it's O1.
Space complexity is constant. Yeah, of course. Yeah, so it's not interesting. Okay. Right. So we talk about binary consensus. The inputs are zeros and ones. The outputs are zeros and ones. So we need to agree on one of the inputs. Yeah. So let's. This is the initial state, and this is the final state. For example, in this case, the final state could also be everybody decides on 0. Yeah, so we know that there's no deterministic solution, FLP. Well, more precisely, we should refer to the paper by Louis and Abu Amara, which is talking about shared memory construction. And we are in the shared memory context. FLP was about message passing. So it's later, 2 years after the FLP paper, there was a paper by Louis and Abu Amara who strengthened this result to the read-write shared memory context. Okay. But it can be done in the abstraction-free way, as we already know. So we refine a little bit model assumptions. Again, we have n processes, reading and writing. So every process is assigned a deterministic algorithm. This is not a strong limitation, as I said already. It's just for convenience. We assume that there is a configuration. Yeah, it's a local state of each process and the state of each register, which we use. Yeah, we only use read and write registers. Well, additionally, we need to talk about initial configurations. What is an initial configurations? It's an input assignment. So we need to give input to every process, because we have now, unlike the problem with counters, where everybody increments and there is just one single initial state, here it depends which input you give to the processes, and this affects the computation, of course. Yeah? So we need to distinguish it. But if we know the input configuration and we know the schedule, the sequence of steps of processes, we unambiguously identify the resulting configuration. Okay? So this is for starting with some configuration C and giving some schedule alpha in P star, which is a finite sequence of process IDs, we get a configuration C alpha. And we know everything about it. We know the states of each process, and we state the state of the memory. Okay? Yeah, of course. No, it's whenever I say register, what I mean is read-write shared memory location. And it's just historically, actually, thanks to Leslie Lamport, we call them registers from his paper of 1978. Oh. Anyway. No, again, the algorithm is deterministic. If you schedule a process and you know the process state, you know where it's going to write, because you know the state. According to its algorithm, we know exactly what it's going to do, which value and where. Because the algorithm is deterministic, the memory is deterministic. So we talk about valency, the potential of a configuration. So anybody, does it ring the bell? I don't know this image here. Anybody recognizes where it comes from? Yeah, well, I was sure about you. So you need to grow up in the 90s to know this. This is from, if you know what MTV is. So this is actually a video from Fatboy Slim, which is called Weapon of Choice. So if you look it up, it's beautiful. But I put it here because it's about potential. So you can choose this, you can choose that. So you always have something to choose. And before you made the choice, everything is open. And roughly, this is what valency is about. Okay? So if you take a configuration, and we can sort of look at the configuration of an algorithm or consensus algorithm. So you wait well, you can look in all extensions of these configurations, and you can look which decisions are taken in these extensions. Yeah. If there is a configuration, well, there is an extension in which you decide V, and there's no extension in which you decide minus V, you would say that this configuration is V-valent, which means that only V and only V can be decided in its extension. Okay, so you look at all possible extensions, and there are infinitely many of them, but it's not the point here. What's important is that every configuration has some valency. It may happen that in some configuration there is an extension in which 0 is decided, and there is an extension in which 1 is decided. Yeah, in this case, we say it's bivalent. Okay? What can we say about valency? First of all, we need to say, well, we need to be able to say that every configuration of a consensus algorithm has some valency. It's either 0-valent or 1-valent or bivalent. It cannot happen that no decision is taken in an extension of a configuration. Why? Because it's an abstraction-free algorithm. We can always choose some process and let it run until it decides. Yeah? So some decisions are always possible. Yeah? So now the question is, which decisions are possible? Yeah? So if some process decides V in the configuration, then the configuration is necessarily V-valent. Why? Because it's consensus. Yeah, you cannot decide 1 minus V if V is decided already in an execution. So in a single execution, there's at most one value which can be decided. Okay? And well, it's actually the same statement reverted. Yeah, no process can decide in a bivalent run. Okay? Sorry? By? No, in a bivalent configuration. No, configuration itself can also bring some decisions. If you look at the configuration, it's a reachable configuration by some execution. You can look at the state of a process, you can see, oh, some process has decided in this configuration. And if it decided V, then the configuration itself must be V-valent. It cannot be bivalent anymore, yeah, because the decision is already taken. Okay? So it's actually, these two are the same statement. Okay, the valency. So you fix a configuration. Configuration is a state reachable by your algorithm through some execution. So starting from some initial state, you take some steps and you reach some state. Okay, so, and state of the algorithm is the state of the memory and the local states of each process. Okay? You can extend it. You can let your algorithm run from this state. And there are multiple extensions. Yeah, it's a distributed system. You have, depending on how you order the steps of the processes, you have a lot of extensions. It's like a tree. And you look in this tree, you look at all possible decisions which the algorithm takes. Yeah, all possible decided values in these extensions. Yeah, well, it's a binary consensus, so these values are zeros or ones. If you can find two extensions, in one extension you decide 0, in the other you decide 1, you would say that this configuration is bivalent, yeah, because the decision is not fixed. You can decide on any of them. If at most one of the two values is decided in extensions, then it's what we call V-valent, yeah, 0-valent or 1-valent. Does it make sense? Okay. So now we, for the purposes of this proof, we need to refine a little bit the notion of valency. So we generalize it slightly. So now we talk about valency not in general, but valency with respect to some set of processes. So we fix a configuration, we fix a set of processes, P, and then we say that P is V-valent from C. Yeah? If in any P-only extension of C, only V can be decided, and not 1 minus V. Okay? What is P-only extension? I only use processes in the set P, starting from C. I don't use any other processes. I only let these guys run and reach a decision. Okay? So it's the same definition, but restricted to some subset of processes. Yeah, and respectively, P is bivalent. If you can decide V, you can decide 1 minus V. You can decide 0, and you can decide 1. In P-only extensions, yes? Well, no other process takes steps. Yeah, of course, they don't change anything. Exactly. Yeah, you can be bivalent for the whole system, but for a subset of processes, you can be only zero valent, for example. Of course. Yeah, but not other way around. Yeah. Okay. So yeah, it's the same. So for all configuration C, for all non-empty sets P, yeah, P should be non-empty to make it non-trivial, of course. Yeah, P is either zero valent or one valent or bivalent. Again, of course, naturally, because it's an abstraction-free algorithm. If P is V-valent, then any non-empty P prime is also V-valent. Respectively, if P is bivalent from some configuration, then any superset of P is also bivalent. Okay? Right, so now I use a few properties. Well, one property is pretty cool. It says if I have a set of 3 or more processes, which is bivalent from some configuration, I can always choose one of them and eliminate it, and still be bivalent. Yeah, there's always some extension phi of C, yeah, in some process Z in P, such that P minus Z is bivalent from C phi. Okay, so it's I start with a big set which is bivalent, and I can make it smaller, starting from some extension of my configuration. Okay. How do I do this? Well, this is a more or less standard argument. So let's assume that we have P of 3 or more processes, which means that you have Z1 and Z2 in P, and there are some other processes. Yeah, it has size 3. Yeah, and I consider 2 subsets. Q1, which is P minus Z1, and Q2, which is P minus Z2. What's important that these 2 sets have a non-empty intersection. Yeah, of course they do have a non-empty intersection because we have at least one guy outside of this Z1 and Z2 in P. Okay? So far so good? So I take this Q1, Q2, and actually I want to show that in some extension of C, some of these subsets of size cardinality P minus 1 should be bivalent. How do I do this? Again, so this is, I'm going to use this kind of diagrams a lot. So you have C. Since C is bivalent, what do I know? I know that, imagine, just, let's say that from this C initially, if I consider C, this Q1 and Q2 are not bivalent. Yeah, so they are the only V is decided in all extensions. Okay. Yeah, of course, if Q1 decides only V, Q2 only decides only V, then a subset of intersection Q1 and Q2 should also be V-valent. Yeah, that's as we know already. Okay, C is bivalent, which means that there is some extension by only P from C in which 1 minus V is decided, yeah, because it's bivalent. Yeah, you decide V here. There is some extension in which you decide 1 minus V by the definition of bivalence. Okay, so I just consider this particular extension, which I call C psi. Yeah, so this is C extended by some execution psi. Okay. So this is the place where you decide 1 minus V, which means that if I run P further, of course I can only decide 1 minus V. So it's a okay, so far so good. Now what I do, I walk through this extension psi step by step, from one configuration to another. I start with the V-only extension by Q1 and Q2. Yeah. I finish with 1 minus V decision by whatever execution I take by V, by P, of course Q1, Q2 also. There must be some critical step where I go from only V being decided to the state in which some of the subsets, Q1 or Q2, should decide something else. Okay, and actually I'm going to claim that it should be bivalent. Starting from V-valent should become bivalent. Okay? What is this critical step? Without loss of generality. Yeah, so without loss of generality, I say that this step is performed by some process in Q1. Yeah, remember that any process in P either belongs to Q1 or Q2. Yeah, because Q1 union Q1 and Q2 is P. Yeah, by construction. So let's assume that Q belongs to Q1. What I'm saying, yeah, so the Q1 and Q2 are bivalent, so Q1 and Q2 are 1 minus V valent. So there is a critical step. So this Q, if Q belongs to Q1, then Q2 must be bivalent. Why? Bivalent from this state, from from this state. No, from this state. So from C prime delta. Delta is one single step of Q. So why is it the case that your Q2 is bivalent from here? Just because Q, this small q is a member of Q1. Q1 cannot be bivalent because this is an element of Q1 already, and we know that starting from here, Q1 is bivalent. Yeah, and this execution, if you start from here, take delta and take Q1 from here, it's the same execution of Q1 from here. And this is by our construction is bivalent. Okay, so the only change which I may bring here is Q2. Okay, Q1 is bivalent from here. Of course, Q1 is bivalent through this delta here, which means that any subset of Q1 is also bivalent, including Q1 intersection with Q2. So the only change which I can get here is Q2. So Q2 must decide something which is not V, which is 1 minus V. Well, naturally, what I conclude is from this configuration on, Q2 is bivalent, because I have a subset of Q2 in which only V is decided, and some execution in Q2 in which a different value is decided, and I'm done. Okay? There are some subtle arguments, but not extremely difficult to grasp, I hope. Okay? So I just play with bivalency, and in fact, what I'm using here is just the notion of valency. I'm not using the memory. I didn't say anything about reading or writing. So this holds for any algorithm solving consensus in any model. What is what? Z is some process, yeah. So this is, in our case, process is Q. Z is Q. Because, sorry, not Q. This is Q2 is a subset of P, and Q2 is P minus Z2. So Z is Z2. Okay? So yeah, I take a strictly smaller subset in which now it becomes bivalent. So actually, I think we're going to use this. So I'll just put it on the whiteboard, just to record it, because we are going to use it. So lemma 1. Yeah, so you start with P bivalent from C. So there exists C. Well, it's not necessary. I just keep it here. So there is this extension of C, which we call phi, and some process Z in P, such that, so this is a dilemma, such that P minus Z is bivalent from C phi. Okay? Yeah, can we go back, please? Thanks. Okay. Now we are going to use reads and writes. Now we're going to use reads and writes. And well, this is we already know. We already looked at this kind of arguments. Yeah, if it happens this way, that P is bivalent from C, some beta, and beta is a block write by some process R, yeah, subset of P. Yeah, a block write is a sequence of write operations on distinct registers. Okay? Then every deciding schedule C by some process Z, which is not in P, yeah. Of course, P now is supposed to be a proper subset of the whole system, of this whole set of processes. Yeah. Then every deciding schedule by this process Z, starting from C, inserted just before beta, should contain a write which is not covered by R in this block write. Okay? Because otherwise, if we let this process Z running and decide before the block write, and it only writes to the covered registers, we just execute the block write and hide the execution whatsoever. But remember that the execution is bivalent. No matter what this guy decided, there is always an extension in which a different value is decided. Okay? This is actually one of the exercises you should look at to prove this. But the intuition is obvious. Yeah, if you cover some set of registers and you want to decide something, you need to write to something which is not covered. Because if you don't do this, nobody would know that you decided a value. No matter which value. You can decide 0, but there is an extension in which 1 is decided. You can decide 1, there is another extension in which 0 is decided. Okay? So this is one of the steps which are going to, one of the facts which we are going to use to establish the lower bound. Okay? Any questions so far? Yes. Mm-hmm. Yeah. Okay. So this is my yeah. So so we have C. Let me. I keep this for future. So we have configuration C, yeah, which is some configuration. We know that C extended with the block write beta is bivalent. So this is bivalent. Yeah, bivalent for some set P, which is actually a proper subset of the whole set of processes. Yeah, it's important because I need one more process there. Okay. Now what I do, I take some Z, which is not an element of P, and let it run before beta. So this is by Z. So what I'm saying is that if this process Z in this execution decides on a value, so this part is block write by R, which is subset of P. Okay? So if Z decides some value V, decide V. Okay? Doesn't matter which value. What's important, it decides on something. Then Z must write to something which is not covered by R. Okay? Because otherwise, nobody would see what Z decided. Sorry? Well, I'm not sure. Well, can we come back to the slide? I'm so kind of curious what's... So any deciding schedule of C by Z not in P should contain a write not covered by R and C. Yeah, when you say covered in C, it means that in C there are R processes in set R which are about to write to some registers. Yeah, this is what I mean by covered in C. Yeah. Okay. Any more questions? Okay. So this is I don't give any proof, but yeah, I think you can prove it yourself. It's not something which is very difficult. Okay. Well, now okay. So we used one lemma which shows that you're starting from a big set of which is bivalent from some configuration, you can go to a smaller set. Now we do something opposite. It's actually there is a reason to do this. So we start with a bivalent configuration, and we know there is a set Q which is bivalent from C. Okay. And there is a block write by some non-empty set of processes which we call R, and we know that R is distinct from Q. Yeah. Some other processes are about to write to some registers, starting from C. Okay. So I want to show that there exists a Q-only schedule phi which I can insert just before the block write, and get a configuration which is bivalent for R and some process Q in this large set of Q. Okay, so I now initially there was some Q were confused in this configuration C. They didn't know what to decide. Yeah, they were bivalent. They could decide 0, can decide 1. And at the end, I extend this C with some execution phi, and then I extend it with execution beta, which is the block right, and I get again a bivalent configuration, but this time for R and Q. Okay. Well, it's not immediately obvious, but again, we can use this kind of argument. So we start with C. Yeah. We let R run from this configuration C. Yeah. And let's assume that there is some execution in which this process in R, after they complete the block write, they let them run and they decide some value V. Doesn't matter. There exists such a value. Some value is decided by R after they execute a block write. Okay, this is one thing. Then, as we know, this configuration C is bivalent for Q. Yeah, we know that it's bivalent for Q. Q is bivalent from C, so which means that there is some extension of C in which processes in Q decide 1 minus V, a different value. Okay, so let this extension be C again. Use the same notation. Well, of course, if I extend this configuration with a block write and any run of R, only 1 minus V can be decided, because this configuration is already fixing the value. The value is decided. Okay, and again, I use it over and over again, I use this argument of critical steps. I go step by step, I walk through this execution C from C, one by one, until only 1 minus V can be decided in any extension of this configuration by R. Yeah, there is some critical step delta. Well, it must exist because it's the final state is like this. Yeah, so you start with some execution decides V, some executions decide V, some executions decide no execution decides V, only 1 minus V can be decided. And this is my critical step. By some process Q in this set Q. Yeah, remember that C is constructed by it's a Q only extension. Okay, some process in Q takes a step, and the resulting configuration is such that if I extend it with the block write and some execution of R, I only decide 1 minus V. Okay? So this step delta must exist. Okay? What can I say about this step? It cannot be covered by beta. Right? Why? Otherwise, there's no difference from R for R. Oops, sorry. There's no difference for R between this configuration and this one. Because you overwrite everything which is written by delta here. But we know that there is an extension here in which you decide V. So the same extension should exist here. The conclusion, Q must write outside of the covered registers. Yeah, so that R should see the difference. Okay? Well, the conclusion, R union Q should be bivalent from this configuration. Why? Because now you have, it's a block write. Yeah, beta is a block write. It's a sequence of steps, writing steps on distinct registers. I can permutate them arbitrarily without actually seeing the difference because they're all distinct. They're completely unrelated. If I add one more write on a distinct memory location by Q here, I have a block write of one more write, and I can permutate, nobody would see the difference. And in fact, indeed, this execution C, psi, beta, delta, and execution C, sorry, not C, C phi, beta, delta, and execution C phi, delta, beta are completely indistinguishable for processes in R, for processes in R union Q, actually. Which means that this particular configuration, C phi, beta, delta, is bivalent. Because you can decide V here, and you can decide 1 minus V here. And we are done. Okay, so we can somehow extend, well, change the set of confused processes to the set of processes who execute the block write. And actually, I'm going to memorize this too because I'm going to use it later for the proof. So I just put it on the whiteboard for future references. So this is our lemma 3. Okay, so please don't switch because otherwise I might forget what to. No, lemma 3. So we were saying that the Q is bivalent from C, and beta block write by R, and Q and R are disjoint. Okay, and well, then there exists Q only phi and Q in the big Q such that R and union of Q bivalent from C phi beta. Okay. Sorry for the writing. Okay. So right. Any questions so far? Okay. So yes.
What is meant by Q only schedule?
Oh, Q only. It means that only processes in Q participate in this extension from C.
But then you talk about R processes being bivalent.
You see, okay, in
C.
this execution, so this is execution C, psi. So this particular execution is Q only. But at each step, there is another path. Yeah, I can remember that we consider a tree of executions, of possible executions. So I can fix a configuration, I can consider multiple extensions. So in this particular case, for example, I fix extension of C, which I call C phi. I can consider the extension of C phi with a block write of R, because R doesn't participate in this queue. R is disjoint. If R is about to write to some registers in this block write beta, they are about to write to the same registers in this configuration too, because they haven't changed their local states. They're not members of Q. Okay? So that's why I can consider this particular extension. And it's still going to be a block write. I can consider this extension, I can consider this extension. It's a subset of a tree of executions. Okay? Okay, so we made all necessary preparations. Now we are almost ready to finish the proof. And this is the goal for us. And we proceed by induction. And by induction is slightly more complicated because now we use, in addition to covering, we use this tricky notion of valency. Okay, what is our goal? We want to show that if we have a set of two or more processes, and this set of processes is bivalent from some configuration, so what we can do, we can factor out a pair of processes out of them, yeah, which we call Q, yeah, and we can extend this configuration C with a P-only execution, whatever alpha, yeah. And we show that Q is bivalent from C alpha, but additionally, all other processes are covering distinct registers. Okay, so it's a strong statement. I say whatever bivalent configuration I consider, I can only preserve bivalency for two out of them. Okay? And put everybody else busy writing to some distinct memory locations. And remember, our goal is to establish a space lower bound. We want to show that certain number of registers are needed. Okay? So specifically, if P is n, yes, if you take this set of all processes, yeah, all processes are bivalent from some configuration, then we're almost done. Well, our goal was to establish the lower bound of n-1. Yeah, here we're almost done. We establish a lower bound of n-2, yeah, because we take 2 out of n processes, let them run and let them be bivalent from some configuration, and the rest is poised on writing to n-2 distinct registers. Okay? So this is our, intuitively, this is our goal. And we proceed by induction again. By induction on the size of the set. Okay? But the base case is almost immediate. Yeah? Why it's almost immediate? Because it's consensus. Let me finish and I'll come back. So imagine that we have an initial configuration of two processes. Yeah, let's say P is of size 2. We must show that such a configuration exists. And in fact, we don't care any longer about anything outside of P because, you don't have to cover anything because P already contains only two processes. Yeah? So you don't. So this part is trivially satisfied because we don't have to cover anything. We need to check bivalency. How do we know that there exists a bivalent configuration for two processes? Easy. We consider a configuration in which P0 proposes, we have two processes, P and Q, P proposes 0, Q proposes 1. If P runs in isolation, it can only decide 1. If Q runs in isolation from this initial state, it can only decide 0. So naturally, your initial configuration is bivalent. And this is the base case. And your question was? Covering. Yeah. When you say that some register is covered in a configuration, it means that there is a process in this configuration which is about to write to this register in its next step. It's not written yet. Yeah, this is the danger. The danger is not when you write to something. The danger is that someone is about to write where you are about to write. If you write somewhere and someone overwrites it, nobody notices you. Okay? So the covering is an important notion here. Yeah, so it's a potential of writing. Yeah, someone is about to write. Will write in the next step. And what's important is in this kind of protocols, if you extend your execution arbitrarily with steps of some processes without involving this covering process, it's still covering this register because its local state doesn't change. Okay? It's an asynchronous protocol. The only way the processes communicate is through reading and writing in the registers. Yeah, there's no back channel where you just tell them, oh, look, I did these steps, you can do something else. Yeah, exactly. And the extension of this protocol in which someone would write to this register. And I think we've covered the base case, and we proceed to the induction after the break. Okay, thank you.